in this session we are going to discuss about impedance matching. Now what is an impedance matching? Impedance matching is nothing but to match the load impedance with the source impedance. So for efficiency and for maximum transfer of power from the source to the load side, we need to match the load impedance with that of the source impedance. Now there are two impedance matching devices. They are, the first one is lambda by 4 line or quarter wave transformer, and the second one is stubs. So stubs are nothing but a section of a transmission line. So it may be a short circuited stub or it may be an open circuited stub. So now in this session we are going to discuss about the impedance matching using short circuited stubs. So let us discuss what is a single stub impedance matching. Single stub impedance matching. So what is single stub impedance matching? Here in the case of single stub impedance matching, there is only one stub which is connected in parallel with the main transmission line, so that the load impedance can be matched with the source impedance. So let me draw the diagram for this single stub impedance matching. Here, draw the main transmission line, single stub impedance matching, and connect a short circuited stub across the main transmission line. So this is a finite line which is terminated by a load impedance ZR. The length of this line is L, and a short circuited stub is connected across this main transmission line. So this is a short circuited stub. Now the distance from the load impedance to the point of attachment of this stub is, it is written as L suffix S, where this L suffix S is nothing but it is the location of the stub, and the length of the stub is taken from the short circuited end to the point of attachment of stub. So LT is the length of the stub, and LS is the location or position of the stub, So now, since the stub is connected in parallel with the main transmission line, actually we know that the short circuited line, it contributes purely an inductive reactance. So it offers only a reactive component. Short circuited impedance offers purely a reactive component, and it is connected in parallel with the main transmission line. So the stub has to be connected always closer to the load. So the thing is, at the point of attachment of the stub, the conductance value, it has to be 1, and the susceptance, it may be anything. So now, since the stub is connected in parallel with the main transmission line, we are going to deal the parameters in terms of admittance. So I am going to write this as ZR. Instead of ZR, it is YR, and instead of ZS, it is going to be YS. Now, at the point of attachment of stub, the real part of the admittance, it must be 1, and the imaginary part of that admittance, it may be plus or minus JB. So let me explain this single stub impedance matching using Smith chart. Now we are going to solve a problem for this particular topic using Smith chart. So what is the Smith chart? So Smith chart, it was invented by Dr. Smith. It is for plotting an impedance, to convert an impedance into an admittance, to find out the reflection coefficient, to find out standing wave ratio, and so these are the various parameters that can be calculated using the Smith chart. Smith chart, it comprises of two sets of circles. One is called as R circle, which is resistance circle, and the other one is reactance circle. Smith chart, it comprises of two circles. One is resistance circle and the other one is reactance circle. Resistance circle is denoted as, it is in small case R circle, and reactance circle is denoted as small case lowercase x circle. So the various properties of Smith chart are, the first property is we can plot an impedance. We can plot an impedance, convert an impedance to admittance, convert an impedance to admittance, then the third one is movement towards the generator, then movement towards the load. Now, movement towards the generator, it corresponds to moving in clockwise direction. Movement towards the generator corresponding to moving in clockwise direction. Clockwise direction. And movement towards the load, it corresponds to moving in counterclockwise or anti-clockwise direction. So let us solve a problem to understand this single stub impedance matching. So design a short circuited stub to match the load impedance ZR, which is 450 minus J 600 ohm, with the load. Design a short circuited stub to match the load impedance of 450 minus J 600 ohm with that of the characteristic impedance, the line impedance, which is 300 ohm. So we need to design a short circuited stub. So designing a short circuited stub means we need to find out the two parameters, namely location of the stub and the length of the stub. So these are the two parameters to be calculated. Now the first step to solve this problem is normalize the given load impedance. Normalize the given load impedance. Normalize the given load impedance. Divide ZR by Z0. That means divide 450 minus J 600 ohm by 300. So that we will get 450 by 300. So it is 1.5 minus J2. So this ZR by Z0, it is designated in lowercase letter ZR, which is the normalized load impedance. It is a dimensionless quantity. So now this is to be plotted using the Smith chart. So always you have to remember that when you solve any problem under stub matching using Smith chart, we need to use the chart as an admittance chart. So we need to convert this load impedance, the normalized load impedance, into an admittance. So this can be done, this conversion can be done either theoretically or it can be done using the Smith chart. So now I am going to explain the conversion of load impedance into the load admittance using the Smith chart. So here, this is now the Smith chart. You have the outermost circle, which is that it is written as wavelength. First step you mark the two ends. Mark this as A and this right side as B. And then here in your chart it is written as wavelength towards generator, clockwise direction. So 0 is written here, 0, 0. See the outer reading, 0, then 0.01, 0.02, like that. When you move in clockwise direction, when you reach the other end, half rotation of the chart, it corresponds to 0.25 lambda. In terms of lambda, you must put the length. So for full rotation of the chart it is 0.5 lambda. And next you will have another circle, which is the angle of reflection coefficient, and the angle of reflection coefficient. Reflection coefficient, it is a complex quantity, so you will have the magnitude of the reflection coefficient and the phase angle of the reflection coefficient. So the next circle, it is angle of reflection coefficient. And then you have another circle, which is the R. You will have set of R circles. R circle, R circle. This is R equal to 0 circle. R equal to 1 circle, it passes through the center of the chart. Actually, draw a horizontal line. So you have here the value for R is, it is very high. So this end is designated as open circuited end. The right side of the chart is actually this open circuited end. But when you are going to use the chart as admittance chart, the other way, the right hand side of the chart is designated as short circuited end. So now you mark this end. We are going to use the chart as admittance chart. Remember, this is very, very important. Admittance chart. So this is the short circuited end. So here you have the resistance circle. No, it is R equal to 0. And then you have R equal to 0.1, like that. 0.1, 0. Along the vertical, horizontal axis, you could see the circle values. R equal to 0.1, 0.2, 0.3, and like that. You will have R equal to 1 circle. It passes through the center of the chart. So which is the matched load condition. So this is R equal to 1 circle. It passes through the center of the chart. So this is R equal to 1 circle. Mark the center of the chart as O. R equal to 1 circle. Now, the normalized load impedance it is found to be, I write the load here, it is ZR is 450 minus J 600 ohm in the given problem. Z0 is 300 ohm and the normalized impedance is found to be 1.5 minus J 2. It is a dimensionless quantity. So an impedance, normalized impedance can be plotted as a point. So it is the point of intersection of R circle. R equal to here 1.5 and X reactance is going to be, it is minus J2. The reactance is minus 2 it is. So we have the R circle as, first you locate R equal to 1.5 circle. So along the horizontal axis you could see the value for R. So R equal to 1 circle passes through the center. So it is 1 circle. We have already marked the center of the chart as O, and then you locate that 1.5 circle. Let me write, this is 1.5 circle located. Now the point of intersection of R equal to 1.5 circle and X is equal to minus 2 circle will locate this normalized impedance. Now the reactance, it can be either positive or negative. In this case, reactance is X is minus 2, it is negative. So we have to consider the set of circles lying below the horizontal axis. So here you have 0, 0.1, 0.2 like that, and you consider the circle which is lying below the horizontal axis. Let me take this. This is X equal to minus 2 circle. So this is minus 2 circle. Here you can write minus 2. Minus 2 is here. We consider, since the reactance is negative, we consider the set of circle lying below the horizontal axis. Now, this 1.5 circle and this is 1.5 circle. This is 1.5 circle. And this is X equal to minus 2 circle. So 1.5 circle and this X equal to minus 2 circle, they intersect at a point. You locate that. So mark this point as P. We have plotted now this normalized impedance on the chart. It is 1.5 comma minus 2. Now the second step is step 2. Note it down. You draw the SWR circle. Draw S circle or SWR circle. Second step. How will you draw SWR circle? With O as center, OP as radius, draw a S circle. Draw a circle. This is S circle. So we have drawn now a circle with O as center and OP as radius. O as center, OP as radius. Now we need to use the chart as admittance chart. So we have to convert the normalized impedance into an admittance. So what we have to do? You find the diametrically opposite point of this normalized load impedance. For that, join this point O with center and you produce it. So now this point P is joined with center and it is extended. Now this point, the line, it cuts the SWR circle at this point. So this gives the normalized admittance. So it is not necessary to locate the corresponding conductance and the susceptance value. So it is enough if you mark this normalized admittance as YR. So the diametrically opposite point of The normalized impedance which is plotted in the chart is now it is nothing but the normalized load admittance. Next step is we need to find the intersection of R equal to, that is G equal to 1 circle and the drawn SWR circle. Find the intersection of G equal to 1 circle. Now we are going to use the chart as admittance chart. That is why I am using the word G instead of R. G equal to 1 circle. Reciprocal of R is G. So intersection of G equal to 1 circle and the drawn SWR circle. So here there are two intersecting points. You mark the two intersecting points. This is one intersecting point and here is another intersecting point. These two are the intersecting points. Now you find you write the admittance value, normalized value from the chart. It may be a value 1 comma, whatever you are getting here you write 1 comma. For example, let me tell you it is 1 comma plus j some 0.8. Let me write. And here diametrically, here just the opposite to this point, let me say it is 1 comma minus j 0.8. Right? Now we have to locate or position or place the stub closer to the load. So here is the load admittance. You move from the load in clockwise direction and locate the point, the intersecting point which comes first. So now here is this load admittance YR. When you move in clockwise direction, this intersecting point it comes first. So you join it with center and extend it. So the distance between now the load and the location of the stub is designated as position of the stub or location of the stub. So this distance. And then in order to, after connecting the stub it contributes only susceptance. So it has to offer and a susceptance value which is opposite to that of the susceptance at this intersecting point. So the stub has to contribute how much of susceptance to nullify this? Minus j 0.8. So you locate the circle on, which is lying below the horizontal axis. So minus j 0.8, it may come here. It may come, let us assume that here is minus j 0.8. So you join it with center and you extend it. So here is this is the short circuited end. So now this distance from the short circuited end to this point, let me write this point as some C, and this distance between B and C is now designated as length of the stub. So you locate the value on the outer scale, the wavelength scale. Note it down, and this value, the wavelength scale at this point C minus the value of the wavelengths at this point, short circuited end, which is 0.25. So you will get the length of the stub. And to designate these two points as this is P sorry, already P we have used, Q and R. So the distance between Q and R, it gives the location of the stub or the position of the stub. To summarize this single stub matching using Smith chart, the first step is we need to convert the given load impedance into a normalized impedance. For that, we have to divide the given load impedance by the characteristic impedance of the line. Then, using the chart, we can convert the normalized load impedance into normalized load admittance, or we can do the theoretical calculation. Theoretically, how will you do? Once ZR is found out, it is 1.5 minus J2. So, YR is the normalized load admittance. It is the reciprocal of ZR. So, it is going to be 1 by 1.5 minus J2. You can make use of a calculator, or you can do manually to find the normalized load admittance. Here I have found out the normalized load admittance using the Smith chart. So first step, you mark the center of the chart as O, then you plot the given the found out normalized load impedance as the point of intersection of R equal to 1.5 circle and X equal to minus 2 circle. So after plotting this point, with O as center, OP as radius, draw SWR circle. And then to convert the load impedance into an admittance, you join this point B with P with the center O and extend it. So find the diametrically opposite point. So this point, it gives the normalized load admittance. So now we are going to make use of the chart as admittance chart. And then you find the intersection of drawn SWR circle and this are equal to one circle. So there are two intersecting points. Locate the two intersecting points, and then from the load admittance, from the normalized load admittance, from in this wavelength scale here, you move in clockwise direction and identify or locate the intersecting point which comes first. In this case, when we move in clockwise direction from the that is, when you move in clockwise direction, you will get this point as the first, it comes first. So this is the place where we should connect the stub. So you join this intersecting point with center and extend it. So now you name this point, intersecting point on the wavelength scale as R. This line, it touches the wavelength scale. So this is R and this is Q, and this distance is now designated as location of the stub or position of the stub or distance between the load and the stub. And then we need to nullify this susceptance. For example, I have written this value 0.8. It may be anything, you have to check it from the chart. So for your understanding, here I have written plus J 0.8. It may be some other value from the chart. So we have to locate the susceptance value, that is, which nullifies this plus J. So below the horizontal axis, locate minus J 0.8, join it with center and extend it, right? And then you name this joint line with the rim of the chart as C here, C. And already we have marked the right side of the chart as B. So now the distance between these 2 points B and C is, now it is denoted as length of the stub. So this is how we find the position of the stub and the length of the stub for impedance matching. I hope you all have understood this concept of impedance matching, and here impedance matching is done by using single stub impedance matching. Thank you.